or maybe for this week at the end. Okay. So
is the homework 7P due today? Because there's no link for it.
there is no link.
No, there hasn't been one all weekend.
Wow. So let me check that immediately. Yes, you're right. There is no link. So this is it, 7P. You see, as you can see here, I already programmed it, but I forgot to click something. But the date is here. So let me edit the options. Okay, this is what I did not.
Can we get an extension for this?
Yeah. So we'll put it. We make it to be done for tomorrow. Okay. So let me the options. So then instead of Monday, we put it Tuesday, February 9th. Now I need to change the, so it's display there, it's okay. Display onto Wednesday, due date, Tuesday. So it's already on Tuesday. Okay, so look, after due date, you can go back to the homework and check if short test results and feedback to students. So during submission, you can get some kind of feedback, and then after due date, you can see the whole homework. Okay. So now they are both there, all right? Fine. So we were looking this, so this is going to be due 9. Yeah, question?
Do you say we should see both the assignments now? Because I just see the 7P.
Well, the other is gone.
Okay.
AQ was on Saturday and plus 24-hour late. So you should, yeah, so it's gone now. Okay. Then the this is the attendance. Okay. So then please roster your name on the chat for the roster. Fine. And then remember on Wednesday, we have our speaker. He's going to speak about right here. Mr. Tony Nicanor, professional engineer, will be talking to us about procurement, design, and commissioning of LED lighting and controller system. Fine. Okay, so then let me put this out. Talking about the LED, let me stop sharing. I would like to find, let me see if I can find, where is it? Where is it? Why is LED important? Let me see, what is it? Lighting system. Where are they? Light sources, okay, right here. LEDs, okay. So let me share this now. Okay, so some data last year on lighting systems. There are about 6 billion screw-in sockets in homes across the United States. 6 billion, okay? So there are 300 million inhabitants in the United States. So this is about 20 times the number of inhabitants. 2 billion to 3 billion of those still have an inefficient incandescent or halogen bulb in them, says Mr. Horowitz. If every home in the country switched those sockets to LEDs at once, we would save an estimated 38 million tons of carbon dioxide emission a year. That's equal to the emissions from about 7 million cars. And it would save money because it means that the US would spend about $14 billion less on lighting annually. On average, every household would save roughly $100 per year in the electric bill. Precise cost savings would depend on a few variables like electricity rates. Okay. The upfront cost of LED tends to be higher than traditional bulbs, but that is rapidly changing as technology improves. And over their lifetime, LEDs are almost certainly a better value because of the energy savings and because they don't have to be replaced as often. In energy, we don't get a lot of free lunches, Dr. Hittinger said, but LED lighting switching is basically a free lunch. Okay, so that's one. Now let me open this one. So that's the distribution of lighting sources according to technologies in US homes. in the year of 2016 is just percentage. 6%. So most of the incandescent few homes use it. Halogen incandescent, those are very bright, very hot lamps. Halogen, they are it's a gas discharge, so it's very hot. Okay, and then compact fluorescent. So those are the tubes, weir form, and then the LEDs. Excuse me. Okay. So there you have these two. So let me, so now what do I want to share? Okay, so then I want to go to my, hold on. Okay, you can see my formulas. So let's do work the problems. So the homework problems are 2, 4, 6. So let's do 1 and 5. So one is, it says 1, figure 6, 120 volt, system impedance 0. Let me make the the sketch. So we have 120 volts, C source, and .1. And what is it? 1.5 load. Calculate A, okay. So calculate A, that's the diagram. Figure 6.1. Yeah. So it says A, calculate normal load current. What's I load? Okay, so that's I load. Then so that's 120 over 1.6. So according to this calculation, that's got to be 75 amps. So this is very simple. Then B, calculate the short circuit current. So if a short circuit current occurs here, let's put a switch here. So if the short circuit current occurs there, then B short circuit current equals 120 over 0.1. So that's 1200 amps. Then C, it says per unit values. Okay, per unit values. So when we say per unit, the first step is define base values. Base values, okay? So in this case, we need B base. So naturally, pick up 120. And then we have several choices. We can, for example, E base, we can make that equal to I load, which is 75 amps. 75, sorry. Okay. We only need two because we can derive C base, which is going to be Ohm's law over the base quantities. So that's 120 over 75. For example, in this, then we can get 1.6 ohm, right? Okay. So therefore, now we have a circuit like this. One per unit here. Now we get the C, the first cable resistance, which is the wiring per unit. So now we must divide 0.1 over 1.6. So therefore, this is going to be 0.625. Okay. The load, C load per unit, then would be 1.5 over 1.6. And that is equal to 0.9375 per unit. So now we can calculate the short circuit current per unit. So that's the voltage divided over, so this is 0.625, 0.625. So then that is 16 per unit. Therefore, the short circuit current now in amps, so let me put here amps. Is going to be the short circuit current in per unit times I base. times I base. Look. So this is the basic definition. So I base is in amps also. Okay, so then we multiply 16 times the base. What was the base? It's right here. 75 amps. Here is the base. So put that here. 1200 amps. Okay. Now, the next problem is number 5. It says repeat problem 4. The transformer is 1500 kVA. Impedance is 5%. Primary feeder impedance is 0.5. 4. So let me put the numbers now. It says refer to figure 628. So 6.5. So we have this figure. Transformer, secondary, and then different loads. Okay. So this transformer in this problem 5 is 1500 kVA. Impedance 575%. Primary feeder impedance 0.75. So this is the utility impedance. So then here we have the feed. Okay, so then it says now we need the voltage. Hold on. Secondary voltage is 480 to 77. So here, okay, that's the secondary. So then problem 4. So he wants to calculate the short circuit current in the secondary. So then we have ground. We need a ground here. And we need a fault here, an F. Okay. So the first step is calculate the base current. Well, we can calculate at primary and or secondary. So in this case, at secondary. So we call it that I2 for secondary base. So we can use the nominal current, which is going to be 1500 K divided by the square root of 3. And now I put, so this is BA. Now I put 0.48 KB for the secondary. So that's going to be the nominal current, okay? So let's do this calculation. 1500 divided by the square root of 3 divided by 0.48. So this is 1804 amps. Okay, so now that we have this, the circuit is substituted by just impedances. So we have 0.75%. So how many need to put that in per unit? So this is 0.075, like that. And then this is 0.0575. And then here we have 1 per unit. So this is the beautiful thing of the per unit representation. All this has been substituted by that. And it's primary, secondary collapse together. We just put one terminal here, the other terminal here, which is primary to secondary. Okay, then we have the loads, the different. And then we have the fault here. Therefore, the short circuit current per unit is just to be 1.0, the source of voltage, divided by 0.075 plus 0.75 0.575, like that. So that sum is 0.560, like that. Correct? I think so. So I short circuit per unit is equal to 15.38. So now I short circuit is equal to 15.38 times 1,804. So then this is 27,757 amps. Huh. However, the result from the book is not that. It's 32,000. So so I have something wrong, okay? What would it be? 5 is 0.75%. So the only thing that 0.75 over 100. No, but this is correct. Plus I cannot see where the error is. 1500. No. Times. Huh. Okay, so I let me just check again the end of chapter. At the end of the chapter, at the end of the book, we have the answer to odd. Chapter 6, 32,800. We are doing problem 5. Oh, sorry. I know. We are doing problem 5. I found the problem is, this is, sorry. This is 0.5%. And then this is 5%. Yeah. So that's what I had wrong. So now here short circuit is equal to 1 over 0.005 divided over 0.5, 0.55. So short circuit current per unit 1 over 0.55. So this is 18.18. So now I per unit 18.18 times. This we did not change. Only the impedance. Okay, so then $32,804. Okay. So that's okay. That's good. Fine. So now let me do something else now. I want to show to you a calculation that I did for the inverse time characteristic. So here in this graph, which is section 7, inverse time. So it says that in this graph, they plot time in the vertical and current in the horizontal. So the curve is called inverse time. And then this vertical is called instantaneous tripping characteristic. So here the logic is like this. If the current is higher than this value, the protection should immediately curtail the conduction of current. So that means instantaneous. In no time, the current should go to zero. Now, if the current is not so high, then the system can wait, take some time for the protection to work. So this is inverse time. So I wanted to show you how do we get the inverse time current characteristic in a fuse. Now for fuse, I mean a small piece of wire, okay? So then we can think about a small piece of wire. So you will have L, length. You will have cross-sectional area A. It be conducting some current I. Okay, what else? Well, now let's look at the composition of the wire. So we have rho, the mass density. What else? We have the conductivity, electrical conductivity. We have the temperature. That wire is going to melt, so that we have a melting temperature in centigrades. And then we have something else, which is the C, the heat capacity. So the heat capacity is the amount of heat that should be provided, fed into the wire, so that the wire can increase its temperature by 1 degree centigrade. Okay, so then the heat capacity is the quantity of heat, which is joules, its energy, so that it can increase per unit kilogram, per unit mass. So that's the heat capacity, okay? So good. So we have two laws or two equations. So first is the let's put the what is the heat of source? The source of heat. So the source of heat is the electric current. So therefore, this is the power, the amount of energy per second. So now we multiply by time. So now we have an equation for energy. Okay, then we will substitute here the value for the resistance. So then this is length divided by conductivity area, I square, and T, time. So we have this expression. Next, we do have the second law. No, it's not the second law. The first law of that beautiful subject which was the first systematic study of energy that was done by the engineers and scientists in the 19th century, which is thermodynamics. Okay, so first law of thermodynamics says that it's the conservation of energy. That's the first law of thermodynamics. So it says that the amount of heat, delta Q, is equal to the mass to the heat capacity times the increase in temperature. So now that mass is going to be the mass density times the volume. Now the volume is LA times C times delta temperature. So this is the second equation, okay? So we need to equate these two equations. And then on the left-hand side, we are going to have I squared over T equals. So the length are going to cancel. The length cancel. A is going to go square. Okay, so then we are going to have rho C sigma delta T A square. See all that? That's a material constant. Correct? I think so. Okay, so we are almost here. So now let's take logarithms. Log 10 I squared plus log 10 T. Yes, the multiplication, the logarithm of a multiplication is equal to the sum of the logarithms, equals log 0 sigma delta T A squared. Sorry, I need a logarithm here. Okay, so finally, we need our 2 times the logarithm of a power is equal to that power multiplied by the logarithm of the variable plus log. So all these are 10, 0 sigma delta T A squared. Fine. So then if we plot this time I, and we use logarithm scales. So that logarithm scale means this is 1, 10, 10 square, or maybe 0.1, 1.0, 10. We are going to get that. A straight line. Fine. So that's the demo of why there is an inverse time characteristic. So this demo is ruled by physics. Okay, so now let me share with you this document right here. So look, here is the material data. Forget about the K right now. We have different materials here: copper, silver, aluminum, chromium, zinc, lead. And then we have the mass density. So lead is the most heaviest, is the heaviest, lead, then followed by silver. Then we have the conductivity. So which is the best conductor? Silver is the best conductor right here, followed by copper. Okay. So then comes the heat capacity. So which material can hold more heat without getting very hot? That's what it means. The amount of heat that it can get, that it can store without getting very hot. So the best material is aluminum. Incredible. Okay. The others, is that right or not? Yeah. Okay. That means it has a high capacity. If you, yeah, the amount of temperature is going to be inversely proportional to that C. Okay. So then aluminum. And then the melting temperature. So this is also very interesting. Chromium, it takes 1400 degrees. Copper. So which one is from the point of view of technology, melting temperature means the engineering design of the pot where you are melting the material. So the one that is less higher temperature is the one that you can do it on a very simple pot, whereas the others must have a lot of insulation in order not to burn yourself. So that's what it means, the melting temperature. So copper and chromium are above 1000 degrees. Okay, then here we have the multiplication of that constant, the multiplication of density, conductivity, thermal capacity, and melting temperature. And then multiply by A squared. So look, it's very sensitive to the area, to the cross-sectional area. Okay. So now I put here, for example, the area of different wires, conductors that we use in electrical installations. So number 10, which is good for 35 amps in a conduit, is going to have 5 millimeters square. Number 8, 8 millimeters square, the conductor. Okay, so from this data, we get this curve. Very nice. I put the current. How did I do this curve? I put the current and then the logarithm, and then calculated the time using this formula. So see, you can see in the formula bar is 2 times the logarithm of current plus a log 10, the material. Okay, so then here is the, and then I did that for 3 materials. One is copper, AWG12. Then next is again copper, AWG10. So W10 AWG needs more current to melt. For example, if you take one here, so this is 1 second. In 1 second, copper, you need more than in 1 second, it says, which is 1 0 here, you need about, well, more than 1,000 amps for sure. More than 1,000 amps in 1 second. Now the bottom is chromel, which is cheaper than copper. Okay, so then in 1 second, you can melt a wire of chromel according to this model with maybe 200 amps. Okay. So this course is going to have a lot of this type of current characteristics. Let me show you a few of them. They look awful, but then we need to understand them. So this is some of them, see? It says clearing times, melting curves. It says amps. It says seconds. And the title is melting and total clearing times, current characteristic for underground labs, class T, 600 volt fuses. So that's only one. That's only the first one. So now if you go to fuses, look, coral fuses. These are medium voltage type. And then here you have again the curves, look. Curves, more curves. Okay, so I wanted you to understand why are these curves like this. So that's fuses in the chapter of fuses. Now, if we go to the chapter of circuit breakers, so here is the schematic of the open air circuit breaker with arcing horns. Then what are we going to see? Here is the characteristic. Here is again another graph for the characteristics. So these characteristics are at the core of the course, okay? Protection. So this is the instantaneous, and then this is the inverse time. See, so a lot of times, okay. Now, the other topic that I wanted to stress to you was so now let me show you the next graph. Oops. Okay, let me show you the next graph. Hold on. So everybody here? Okay, so then this is the other topic. right here. Fine. So look, this is the asymmetrical short circuit current. So that's also a section, asymmetrical current, short circuit current. So in the book, there is an equation which looks like this. I asymmetry equals IDC plus, I think I need to, DC square. So what happens when we have a current like, which has like, as a function of time plus IDC. So this is effective, okay? Or RMS. That's why I put the square root of 2. So then what is the, this is a total current. What is the RMS of I? So we are going to call it asymmetric, like this. So then the general formula for you need to apply this formula. Which is the definition of RMS. So we need to put I squared here. Okay, so therefore I square. So let me get rid of the square root in a moment. So now we put I square. So we need to do the square here. IAC. Now we put the cosine because it's a sinusoidal plus IDC square over dt. And then this is a square like that. So the square is on the, not there, right here. Okay, so then we have cosine square. So then we have here 2 times IC square cosine square plus IDC square plus 2 times square root of 2 IAC IDC cosine omega t, the double product. So when we do the integrations, we get this term. So we do the integration, we are going to get IAC squared. Next, we have the second term. So that's IDC squared. Next, we have 2 square root of 2 IAC IDC, the integral over the period of cosine omega t dt. So this integral is 0 because it's 1 positive cycle plus 1 negative cycle. The integration, the cosine. So then this is 0. Okay. So therefore, QED comes from Latin, what we have to demonstrate. Those acronyms come from Latin, okay? Question is demonstrated from Latin. Maybe that's it. That's what it means, okay? Fine. So the DC part affects the RMS of the current. So now let me show the calculation. So we are going to do that over a resistor, an inductor, and the source. Resistor, and then J omega L right here. So then this is the current that we want to plot. So the current that we want to plot is, let me write the expression here. I'm going to get it from, it's going to be the source. So if the source is A, E, hold on. Where is C here? Peak amplitude, source voltage, 100. Okay, over the square root of R squared plus X squared. And then there are a lot of terms here. They're going to be cosine omega t A5 cosine omega t minus source angle theta minus impedance angle phi wow. Okay, so that's the first part. And then the second part, well, I don't remember the expression. I have to, it's going to have an exponential minus t. Okay, so next time I'll bring you the equation. But these are the graphs. See, so here I have one graph, which is the source voltage, and it has an angle. The blue. And then the second graph, which is the pink, that's the current. So then we see the asymmetrical current. So for example, if the angle goes negative 90, so then the current becomes initially negative, and it eventually settles at the root mean square value of the symmetrical component. So for longer times, this when the current becomes with a permanent AC value constant, then that's called the symmetrical part. And the asymmetrical part is the transient. So for example, here the transient is higher in magnitude, higher than 20 amps. Now, let me put the angle back to positive. Now, it depends on the angle of the voltage. So now look, the source voltage has its own angle here. So if I put 0 angle, see, incredible. Now the transient goes away. And this is the less severe case of the transient, because now the current is not higher than 12 amps. 12 amps, it can get very high. The worst case is 90. So the current can get higher than 22 amps. And then I put this table here. I calculated the table for worst current. Look, 21.9. Okay. And then the force in the conductors is proportional to the current square. So therefore, for 90 degrees, look, the force can get as high as 2.77. So that's 3 times the normal force. So what force are we talking about here? We are talking about the force of the bars. For example, within the circuit breaker, we are going to have the copper bars. Subjecting themselves to forces. So then they can have a lot of force during the transient as high as 3 times the normal force. So then it can break the let me see if I can find you a picture here of okay, so this is what okay, next time, picture of circuit breaker and equation of asymmetrical current, So that's what I have to do for next class or 1 week from today. That's for the future. Now I think it's time to go. So in this class, I wanted to be explicit with some demonstrations of the asymmetrical current and why it is important for the calculation, because during the transient, this is the inrush current. That's another name. You can Google this as inrush current. The inrush current can be high. Okay, so, and it's important. So that was one question that I wanted to answer. And then the second question that I wanted to impress you with is the inverse time current characteristic of the protection devices, and how the physics of the melting of the piece of wire goes to this type of functional equation. All right, so I think that's all for today. So then remember next Wednesday, the homework, and also the homework is due tomorrow in the afternoon, but then also the meeting with Mr. Nicanor. So let me go back to you and stop sharing, and let me see all your faces, please. And then don't forget to write your name in the chat so that we can take care of roster. So further questions? Okay. Well, thanks a lot. Class dismissed. Goodbye.
Thank you, sir.